So last time we started setting up the formalism for quantum information. Then we looked at correlations. Then we looked at randomness. Actually, I met Nicolas Gisner the other day, and I wanted to show you. He actually gave me a random number generator. So this here is actually one of these experiments I presented to you. And it's apparently in every Samsung phone that you buy in South Korea. Not in ones here, but if you remember that this was like a Hadamard operation, and then you do a measurement. Okay. You do this, you do the measurement, and then you get with 50% probability you get a 0, and with 50% probability you get 1. This Geneva-based company Asymptotic, and they make this random number generator. You can apparently buy the bigger one here standalone, and the smaller ones. Maybe I give it around so you all can have a look. Not how much you see, but then you have like one in your hand at least. All right. So then afterwards we talked about Bell inequalities and quantum correlations, and then we started with quantum data compression. And I want to now take up this point on quantum data compression and how it leads to our understanding of quantum communication theory more general in the sense of Shannon, but brought into the 21st century. And then in the second half, I will talk about multi-particle entanglement. So in some sense, communication that we consider now, or compression, has only to do with two. From here to there, sender to receiver, but you might have more advanced correlations also among more than two, and this is what we're going to do in the second half. Okay, so I will repeat sort of the setup for quantum data compression. This was the setting first considered by Schumacher in the early 90s. It's the following setting that you have a machine that flips a coin, maybe uses a random number generator to do that. And with a probability p phi, it will spit out a quantum state psi. So phi. So p phi with this probability, it will spit out this phi. Then there is some encoder. We want to compress the information. We're going to put it in the storage. And if you remember the wire here.
Sorry, what's written in the box? P
Oh yeah, sorry. Yeah,
comma.
Yeah, no, I'll just write it. So with probability p phi, a pure state phi is being produced. Okay, so a quantum system in that pure state phi.
And those phi's go over some set.
Phi is from so phi goes over some set, exactly. So you can just think of phi being phi 0, 1 could be an example that you go over the larger set. And this phi here is more relevant. It's not so relevant where we set this goes, but you think of this here being a dimension and d is fixed.
So this is it produces some density matrix state.
Yes, yeah, but it's actually now in the way I present it, it's better to think about that it spits out a phi, okay, and then it spits out a phi with a certain probability p phi.
Oh, so you're saying it's all after the measurement. So
yeah, so think of the information of what phi is being accessible to an outside. Okay, so the maybe this is confusing, this notation. I'm sorry, I'm going to change it now. Maybe I call this pi and then phi I. I think it's maybe less confusing.
Are they orthogonal?
No, not necessarily. They're not necessarily orthogonal. No. If they're orthogonal, then it's a classical problem that I'm going. So the problem arises, but no, they're not necessarily orthogonal. So for instance, a famous set of states is called the BB84 states that is being used in quantum cryptography. Copenhagen 94 for their protocol, and it will be the states 0, 1, plus and minus, and the plus and minus states are 1 over the square root of 2, 0 plus 1, and this here is 1 over the square root of 2, 0 minus 1. Okay, so you can think of set to set, or you can also think of the 0, 1, but it's a little bit better if you think of it a little bit more complicated. You can also just take two of them actually, like the 0 state and the plus state would be a good example.
And the PI sum up to 1.
Sorry?
PI sum up to 1.
The PI sum up to 1, yes.
Okay,
So
that's already reassuring.
yeah, it's very reassuring. Yeah, the source flips a coin and then it spits out this. Then we do an encoding, and then we do storage, and then we do a decoding. And then hopefully we get on the other side we get the source as if it was unchanged, right? So what we want is that that this entire box basically is again, right? We want that this is the same as the original source. I'm writing source now in it. Right, then we somehow have achieved our aim of lossless compression. Right, so then we have the same thing, but hopefully we could save some storage, right? Because somehow the size that we need here, if you then is log dimension, and you want so the log d, where d is dimension of the system, and here you want to do something smaller. I'm always taking the log now because then it's better to think in terms of bits. You think of
But again, because last time I was sort of confused, is it you want it to be equal, but in practice you will then make some compromises.
I was just going to start. Yeah, in practice we're going to maybe make some compromises. We're going to make some compromises in a minute. But so this would be lossless compression, okay, or zero error compression, or zero error compression. The first setup, okay, and here we figured out what it is. There is somehow an obvious thing we can do in order to compress. We can look at the span of these here and just project onto the span of them. And then, you know, the dimension of the span of the P phi that appear with non-zero probability, they will actually be, it will be sufficient to care about that. So the solution somehow, the cost is the log of the dimension of the span I will go back. So the compression cost I want to is actually, it turns out, and this is not so hard to see, and I think it's a little bit clear now, is the dimension of the span. And now the span of what? The span of the phi's such that, or phi I such that pi is non-zero. Okay? Of course, I could with probability 0 add something here, right? And then it would look bigger than it is. So so this is the cost here, right? Okay, so that would be my R in this case. Okay? That's the minimal cost. If you project to something smaller, then there's not enough space. You will not be able to recover the symbols. Okay.
But PI can be arbitrarily small, right?
PI can be arbitrarily small, but somehow you see that if we are really claiming we want to have equality, then that's sort of what it is. So you're right. I mean, what you see here is that somehow it doesn't actually depend on somehow how close these states are, or how high the probabilities are, and so on. And there comes, and therefore we need to reformulate things a little bit if we want to study the epsilon error setting. Okay, so that was the zero error setting. So cost, this is zero error, zero error. That was very nice. And that corresponded to an error here. But of course, I could be interested in what is the cost at epsilon error. Okay, what does epsilon error mean? Epsilon error means that that for all I, right, this actually means that for all I, no, it means yeah, it means it on average. So I want so then the source spits out this in general now. So I'm just going to modify it, right? Because it was so here I get this phi out, right? Phi I, get phi out, and then after the encoder decoder, there will be something happening, and then actually density matrix will come out, rho I, in general. And I explained only density matrices very briefly yesterday, right? Last time. So I will best explain this on a different plan.
I'm not sure, maybe everybody here knows about density matrices,
Yes.
or not really.
No, it's okay. I just need to. I want to get the right way of formulating it, because I tried to. Okay, hold on. Let's do it. I will just explain what the error is in this scenario, and then you will see why it will change the way I do it. Okay. So with probability pi, right, I receive a phi I as a state, and the density matrix of the phi I is the projector onto the phi I. I will send that through my encoding, through storage, through decoding, and I receive as an output, in general, a rho I, like some density matrix rho I. And then I could ask, I can say what do I mean by an error, and the error in this coding will be the difference of the rho I to this original state phi I, and I'm using a standard norm to qualify the distance. That's the one norm. It's important that we take the one norm because that has a probabilistic interpretation, and then we take the probability over we take the probability over the output. So this here would be a way of qualifying the error of my coding scheme. And you see that if I put epsilon to 0, what I really mean is that for all, right, then all of the terms here have to be 0, for which the pi is 0. So it means that all of these rho I have to be equal to the phi I. And in other words, it means, like, if I have an epsilon error, it means that when I look at the source and I look at the output, then the two, so this box, okay, this thing here and the original source, they will be indistinguishable. They will be indistinguishable up to probability epsilon. Okay? So if I have to guess, if I'm given this box or I'm given the original box, then with probability epsilon, I will only be able to guess it with a bias of of epsilon. I guess the word bias is now very ubiquitous, so use it, right? So with the bias will only be epsilon in actually testing which one it is. So you will be able to guess is this or this with probability half plus or minus epsilon. So this is a way of quantifying it.
Sorry, but what is the cost at epsilon?
Ah, the cost, yeah, well, we haven't computed it, right? So then we have to compute the cost, right? For that scenario with an epsilon error.
What is the definition? What is the definition of in this case?
Ah, the definition is the same. The definition is the minimum R, but now you have this epsilon criterion, right? That this should be smaller than epsilon. Okay, so you have a weakened criterion, and because the criterion is weakened, you can get a better storage rate. This is the idea.
But it is still the log of dimension. So
No, that was the result. Okay. So, okay, this is very important. This here was, this was not the definition, this was the theorem. So the definition was, right, the definition of the zero error cost was the minimum R such that for well, okay. Yes, so if I make it really formal, it will be very long. So it's the minimum R, such that the I will give this a name. It's the minimum R such that I have to denote the output still by something, right? Such that the output minus phi I, that this difference is 0. So the cost is the minimum of, and the logarithm of it, always taking the logarithm. It's the minimum of the logarithm dimension such that I don't see a difference between this box and this box and the original source.
but this equals 0 thing implies that it's a 0 term wise.
Yeah, it's true. It implies that, but it doesn't necessarily imply that the minimum R such that you achieve.
But R interferes how into this expression?
Through this box. And we really have to write it down now. Right? I mean, I can really make it it's sort of, so we had so what I was explaining at the beginning of the lecture last time, that time flows from left to right, and this you can really view as a quantum circuit that I had explained. And now the quantum circuit, you can, if you that this sort of the quantum circuit can have multiple wires as the output, and in principle somehow it can have more wires that go into nothing, like traced out. Okay, so then I get a completely positive trace preserving map when I do that, but that's again like the result. So you can think of this as a quantum circuit. This is just the identity map, and this is another quantum circuit with these additional wires. I mean, there might be an additional wire coming out here, carrying some. And then this entire thing is a quantum circuit. Does that make sense?
Yeah, but R and interferes through. So which quantity there depends on R? In the
output wire here has dimension R.
Yeah, but in the final expression, in the definition of the cost, So.
Yeah.
Quantity
Such,
depends on-
well, it comes in with the row I.
Okay.
I define the row I as the output of this sequence of maps, where an intermediate map only has an output R. Does that make sense? Okay. And then, right, I didn't now give you a formal proof for this because I think it's fairly, it feels at least fairly self-evident. I mean, I think we went through the classical case. It feels fairly self-evident that there is no other option. If I'm not allowed to make any error, there is no other option than to preserve the entire span of that state, of that space. And if I have to preserve the span of that space, then this is certainly the minimum, but I can also achieve it by namely projecting onto the span of that space and then just like putting the span like in here. So if you want the map here, this encoder will take this span and put it into like, I don't know, the first few columns, right, of my matrix, and then submit it, and this guy will just be doing the inverse. That's the idea. Okay. Good, but what you already now have seen here is that as soon as
Maybe I'm confused by, suppose we have an example, right? With the 0, 1, plus and minus. Right? So that's what
0, 1, plus, minus, yes.
So then for a perfect encoding,
Yes.
I would need 4 states. Is it right? That's what you're saying.
No, the dimension here is 2.
You're saying-
Dimension is 2. You actually don't need to do anything.
Okay.
So it's maybe better if you think of here's another crypto system which is kind of more interesting maybe.
Oh, okay. So the dimension is 2, but I can now read all those states completely from the storage. Okay.
Yeah, but you could think of now a larger system. For instance, you could think of one thing that they also do in cryptography. I'm just, is when you take, we had the singlet states the other day, right? You take like 4 particles, so it spits out like trains of like sets of 4 qubits, and they are in a singlet here and here. And the other option is they're in a singlet this way and this way. Okay? And then you have this like your first state, psi 0, this is your second state, psi 1, say, or I call it phi 0 and phi 1. These two states that are not orthogonal, and of course it's only 2 pure states. They span a 2-dimensional subspace, but they live in this 16-dimensional subspace, 16-dimensional space. So then somehow your encoder, what it could do is it could map this 2-dimensional subspace onto 1 qubit, and then it sends that 1 qubit. You can keep it in storage and you decode again. Well, it's maybe a good. I like it. It's kind of quite a nice crypto system, this one actually. And they are, yeah. Okay. Right, but now.
Sorry, yeah, being stupid, but then it sounds like you can map anything to 1 qubit because you do have for 1 qubit, you have an infinity of different states, right? So whatever, yeah, I take phi 1 to phi n, whatever it is.
Yes.
And then I encode it in 1 qubit, as you did here with 4 states.
Yeah, yeah.
So
if you can have infinitely many, sure, yeah.
Mhm.
You can have infinitely many states here. As long as the space is only 2-dimensional, it's fine. You will, it will only be a 2-dimensional system that you need to hold. Also makes sense, right? I mean, you're getting it like this qubit, and it's in one of these infinitely many states.
Mhm.
So you don't need to, you actually cannot really extract them either, yeah, so. Okay, good. But I mean, what I wanted to say now is that what you maybe already somehow you get the feeling that, I mean, and we discussed it when we have this formula, that here in this formula, which is the formula for 0 error cost, you see that that the relation of the states to each other, apart from the entire span, doesn't come in. They could be very close together, it could be very different. So somehow this concept of probability doesn't really play a role in some sense. And we don't use it to make compression. If, however, we want to talk about an epsilon error, we need to convert to we need to describe the source properly in the density matrix formalism, because we want to take that into account, because our probability of error will be tied to whether or not we can distinguish this in the laboratory. So it manifestly has to do with measurements that we can do on the system. And I want to therefore explain how we have actually a better way of formulating it. So this was sort of Schumacher in the 1994, I think. But sort of in the subsequent years, people have sort of like understood that this is actually not a good way of thinking about the problem, or it's maybe not the most general way about thinking about the problem. And why is that? It is, and you can already now see it, it is because it turns out that already in this case, you see that it actually didn't depend on the states. It only depended on the span of the states. And in the same way, this problem here will actually not depend on the ensemble, so the pi and phi, but it will only depend on the density matrix. So if we define the pi, if we define this density matrix, it turns out the solution to the problem will only depend on this average density matrix, and therefore it's appropriate to change it, because we can have different ensembles that lead to the same density matrix, right? So it's like mathematically it doesn't seem to be doing the right thing. Looking at the ensemble, then doing the compression, if like somehow everything only depends on the density matrix. And therefore, and this is sort of an important step, I think it's maybe one of the most crucial steps in the development of quantum information theory, that we sometimes call, we call it sometimes the church of the larger Hilbert space, that you somehow, very often we want to look at a purification of the system. So maybe mathematically it's not so deep, but like conceptually, I think it's very important for our field. So that here, right here, the criterion of the error was depending on this I, right? So we somehow, the source, if you think about it that way, at the output, I have access to the I, right? So if you think about that, the I, the label I flows on a separate wire over here, and I'm asking, is this ensemble pi phi I preserved to be pi rho I? Does that make sense? So it's not like I forget about the I and I only look at the source. Here I have on a separate wire, I have this I. And then somehow I notice, oh, the problem only depends on this. So the big step has come in realizing that you should actually look, instead of looking at a classical wire that spits out I, having a quantum reference system to this. So you basically look at a quantum system.
To be honest, I find it rather confusing, because you're explaining to us what we would have stored if we were thinking about it, instead of like telling us what we are doing. And I'm really confused about it.
Yes. Okay. Maybe I explain it and then I show you the relation to this.
Yeah.
Because, yeah. Okay, so the modern way of looking at quantum data compression would be to think of the source as having a reference system, so that the entire state here is the system, and I call it A now, and the reference together. And this is in a pure state. such that the source up here, so the on this wire here, I have the reduced density matrix, which was rho. So rho is rho A is the trace over R, and then say psi AR, psi AR. Right? So if I look at the reduced, if I just look at the reduced state up here, it is of the form rho.
But it's a different physical model of the source, right? We agree on that. What you were saying before was different. I don't know. You're saying it's a modern view, but it's just a different view. It was not like that. Now you're saying
Yes.
these probabilities, they come from sort of whatever
Yes.
measurement on some other system.
Yes,
Okay.
but I can produce this source from this model
Yes.
by making a measurement on the reference system.
Yes, sure, but like that's what we want to work with.
That's what we're going to work with. Yes.
Yeah, this to me it looks a lot cleaner. The one
Exactly.
before, to be honest, sounded like nonsense, but this one does not sound like nonsense.
But if you think about the classical case,
Yes.
just think for a moment about this classical source. Like I'm speaking, I'm emitting symbols, and they come with a certain, I'm repeating myself with a certain, my symbols come with a certain frequency. You can model it by a certain probability distribution. It spits out certain symbols, right? And then you're asking, then you want to compress this, right, in your brain or in some computer, right, that records this. Here we have one, right? And then you want to make sure that you compress this, and then you reproduce it, and then you want this to be sort of like a proper. In the end, you want this to be the same as this, right? Where's the reference system? I mean, there was no reference system in that description.
Right.
So in that description, somehow I'm only asking if with high probability, what I emitted is the same as what the source, I mean, is what happened after compression and decompression. So this concept of compressing data, like we know it from this, or from taking a file on a computer and zipping it and unzipping it or whatnot. This way of thinking has as a natural generalization the one I explained here. Right? Instead of like emitting classical symbols, I now emit quantum symbols, which I could do by having a very weak laser pointer in my hand, or by anything else. And then we could ask the same question of so it's really that setup. So the step to here, which now feels maybe more natural for people who've studied mathematical physics, that really took a step. I think it's a big conceptual step that happened. And but I think with the community agrees that's the right way of thinking about it, and it allows you to reproduce it by just putting a measurement here.
But we agree this is a particular model. How you before you were saying conceptually what you want to do, but now you're saying, oh, but now I fixed the way how I plan to do it. Is it right?
Yeah, it's a particular model, but it is sort of the model that covers all of these at the same time. Because for any realization, so for any ensemble pi, phi I, with pi, phi I equal to rho A, there exists a measurement. So let's call this ensemble something. So for all, I call this ensemble E, okay, that has this property. There exists a measurement, let's call it ME, such that leading to I, right? Such that this, so it has a classical output, right? This measurement has a classical output I, such that this is the same as the source that I had before, spitting out phi I, and here giving me the classical label I.
On that we completely agree. Yeah, sure. You can always realize it that way, but
Yes.
who knows, maybe in many other ways. For now, you're saying since all we can do in quantum mechanics is measurements, then that's basically the only way how it works.
Yeah, but it's what is important about that statement is that if you start with any representation on the right, you can always view it as this in the left. Okay, so it's this direction.
No, but always in the sense that you would reproduce the outcomes. Yes,
Yes.
but maybe there are many maybe there are many other ways.
No, but I'm sort of like starting
Mhm.
from a source in the traditional sense. It's like spitting out with probably
Mhm.
pi some phi I. And now the claim is for any such source,
You can build such a model.
I can the model is the model is fixed, right? So for any source on the right of this type, where the density operator has the average row, I can now find the measurement such that this reproduces this thing on the right. And in this sense, at least, it's this way of analyzing the source is universal.
Mhm.
And I think this is sort of it's a step. It's also an interesting step technically because if you were to generalize the source to spitting out mixed states, this interpretation doesn't exist, and lo and behold, the problem is unsolved.
Mhm.
So this is an unsolved mathematical problem to analyze sources where you have this mixed state description.
Mhm.
So yeah. Okay, but so this is in the background and sort of like giving us a justification of looking at that way. And then, well, if we understand how to compress, now I would really like to erase, but it's anyway on tape, so I will erase it. So we have understood now, I guess, that the right way of viewing it is to view it relative to reference system. So I erase everything else that was not doing that. So of course, pedagogically not good, but since we recorded it. So I'm left now with studying the source relative. So here I have an encoder, I have the storage, and I have the decoder. And here is the reference. Okay? So now, at the end here, I will have a quantum state, which is some density matrix on rho AR. And what I just want is that psi AR is the same as rho AR. Okay, it looks much simpler than this, but by the fact that I can push this this measurement through, it's the same as over there. So if I have a good compression here, it will imply one over here. So I want that this one here, right, is, and now I can put epsilon error close to, you can put epsilon to 0 if you want, or you can put it to non-zero. So this is the right way, or the modern way of viewing that question. And that just means now you have different ways of thinking about it, but probably good would be to view it as like the trace distance of psi AR being smaller than epsilon. Okay. Okay. So the source, no i's anymore, no states phi. I just ask it for doing that.
And this norm index 1, what is it?
It's the trace norm. So we define the norm of an operator y as the trace of, let's say, y is Hamilton. As the trace of y dagger y, or that's the same as the sum of the I made it Hermitian of the eigenvalues yi absolute value.
But probably it doesn't matter so much, right? The learn that in finite dimensional spaces, all those norms
Yes.
the equivalent, so in principle.
Yeah, but we want a probabilistic interpretation of it, which means that if we're saying this is epsilon close, it means that we cannot distinguish with the bias better than a half. So it's related to the probabilities of quantum mechanics, to Born's rule and the inner product of the Hilbert space. So you can also, instead of this, you could also use 1 minus the fidelity. So in this particular case, right, you can also use that. That will be fine too. Okay, so it's not exactly the same as this, but it's fine too. So there's different ways of doing it, but you should not use the 2 norm, for instance, because as soon as you have as soon as your dimensions grow, it will lose the connection. There will be a difference between the norm and the probabilities, and that will depend on the dimension. And since whenever we do information theory, we will, even though often our problem will be set up in fixed dimension, we will then take maybe n copies of the source, and n is arbitrary. And then suddenly the dimension is d to the n, and then I cannot, I have to use the right norm from the outset. Yes, but it's a good question. Very good. Okay. Good. So then we have the setup. Now we basically have the basic setup that will if you have questions about that, it's a really good point in time now to ask, because it's very important for the rest of the formulation. But basically you have the formulation of all of quantum Shannon theory now, if this setup is clear. So we can do more, and of course also ask later. Okay. I want to do one more thing. Is it clear? So we had here psi AR, right, with some quantum state. There was the purification of rho. I want to do this explicitly. So we have seen the relation between rho and psi AR once, so it's very clear. And maybe I call it rho A also. And what is that relation? So we can, for instance, if we're given very often, like, sorry for this, I'm moving back and forth. Very often, like, it's the source that's given, and then we look at this purification. So it's important to understand how to construct one. It doesn't matter which one, but it's good to know one that we construct. And we do it like this. We take what we sometimes call a maximally entangled state. We take a state that is of this form, and I deliberately now do not normalize it now, because then psi AR is actually square root of rho A tensor identity on phi. Right? And we can verify that. It's not hard to verify, because what was rho A? The claim was that if I trace out R, right, of that state psi AR, then I get back. I get back by rho A, right? So I have to check that. So what I do is I write out what that means. Maybe I'm making one step here, and I'm writing this as trace over this. And now I'm writing this out. This is rho A tensor identity phi times, so there's like 3 operators that are being multiplied, identity tensor rho A, and then the trace goes to trace over this R system. Sorry, this was the wrong way around. Square root of A, and here is the identity of the R system. And now I have to compute this. So for instance, I take now a basis for my R system, and then I'm saying, well, okay, I'm taking this, I'm sandwiching this, right? So compressing this on the R system, but actually I'm not doing anything on the A. So this is now really bracket notation, gymnastics in this form. I'm taking this tensor identity, and then I'm writing out my phi also in this form. So I'm writing out J, and then here I'm writing I. This is on A, this is on R, right? And then I have this was J. And then here I have a sum over K. And then I have K on A. Well, sometimes I put the, and then I have K on R. And then here I have my last term, which was square root of A. Okay, I mean, maybe it's obvious, but I will carry it out now. Then of course I have to close it. And I have to do identity on the A system, tensor, and then I have my closing ket on the with an I, right? Because that was the trace, right? I take the trace on the second system. Okay. Maybe I put more brackets. More brackets. Okay. Does that make sense as a way of tracing out? And then what we see is that, see, this guy commutes with this guy. So I can just swap those two. And the I will contract with the J. Okay, so it gives me a delta IJ. And here on this side, this guy also commutes with this one. And then I have I goes with K, right? So this is the sum, and here is the sum over I, right? This is the sum over I, J, and K, but it's a delta IJ, and I have a delta IK. And then what is, and then they just all annihilates, right? And then what does it say? It just says, well, I mean, it just says sum over IJK, and then it's the square root of A applied onto, right? This was a J actually, and this was a K. But now both of these here are equal to, this was on the A system. Both of these are equal, and then here I have the square root of A also, right? So if this here is J is equal to I, K is equal to I. So it says I here. If I sum over I, it's just the identity. So this is just square root of rho A times square root of rho A, which is rho A. Right? Okay, so it's very sort of small computation.
Product of two square roots is probably just.
Sorry, yeah, of course. Of course, that was
Sorry,
also the claim.
the Yiddish remark.
That was also the claim, yes. Okay, so so this way we can construct this purification, and we have this relation between purification and the state. I think it's very nice that you are familiar with this. I think it's a very nice kind of good. Okay, now we really understand what is going on. Okay, we just have like a running. Okay, and now we can do compression. How are we doing for time?
Yeah, probably soon we should have a break. Right?
So like in 9 minutes?
That's a possibility, or
Okay.
earlier.
Or earlier.
Yes.
Let me have a look what I want to say. I think what I really want to
for instance, the break can be down.
yeah, we can take a break now. Let's take a break now. Good.
Okay, perfect. So thanks a lot. Let's do a break, and we come back in 10 minutes, which is like very shortly after 4.
Okay, perfect.
Thank you.
Yeah, easy, I should say, but.
Okay.
What is the relation with entanglement? Entanglement, you only have two particles.
Yeah, you can think now if you can this and this is entangled.
The recording is running. Okay, perfect. So welcome back, everybody, and let's continue.
Okay, so I think we'll now that we have this setup, I want to probably mostly state results and state a few results, and then we can see in how much depth we want to go. And okay, so the first was this cost, right? That was zero error. And I think from sort of the you know, that actually turns out to be the log of the rank of this density matrix flow A setup. And this actually we give a name, we call it the zero error, we call it the zero order zero Renyi entropy. So this is the order zero quantum Renyi entropy. Okay. Then we can immediately now the epsilon error. Basically, I already know what it is from what we did last time. It is the following, right? So you take the last time we had the probability distribution. You take the eigenvalues of these are the eigenvalues of rho. You plot the histogram of those eigenvalues. Actually, I kind of like to order them so that they ordered according to size. So this is like this is index I, right? So these are the eigenvalues of rho I, and then we put an epsilon error. We just we cut them off at say this total mass here. The mass of this is smaller than epsilon, and then we may look at the corresponding density operator. So, and you can see that this, if you just cut off these eigenvalues down here, you get a new density operator. And that new, or if you cut it, maybe it is not normalized. So actually, it's the minimum. So you're allowing an error, and then you do the zero error coding for sigma A, and the minimum goes over a sigma A, which in the operator ordering is smaller than rho A, but you can just think of this as cutting off eigenvalues. Okay, you can do more general things. And not only it has to be smaller, but we also take the trace of it should still be bigger than 1 minus epsilon. Okay, so the mass that's left on my sigma is bigger than 1 minus epsilon. So you can see that this sort of like corresponds to the concept of cutting something off to reduce the rank of my operator. And so I'm just looking at then this, and then actually you can show that this cost, the zero error cost, corresponds to this here.
So how the width of, in this histogram, the width of
Oh, there's no width. Sorry, there's no width. These are just all indexed. They're all the same width.
Oh, okay.
So does it look like I have different width? No, I just,
So you cut out the eigenvalues smaller than epsilon, right?
yeah, the sum of them small than epsilon, okay?
Not all.
Not individually small than epsilon, the sum is the combined mass I'm cutting off should be small than epsilon. Yes. Okay, and then you can give this a name, right? You can say, well, okay, I'm giving it a name. This is the zero order, the epsilon. This is called the epsilon smooth. And actually, person who really did these formulations is Van Renner from Zurich that really did these smooth Renyi entropies. So epsilon smooth Renyi entropies. So I'm formulating now this formula. And why is it sort of smoother? Okay, because before you see this rank here is not very smooth quantity, right? So I'm adding something a little bit to it and the rank goes up, or I'm subtracting something tiny and the rank goes down. So it's not a very smooth quantity. So if I'm now, but after I've cut off epsilon, then somehow if I'm allowing this cutting off of epsilon, then it's like pretty smooth, at least for stuff that's smaller than epsilon. That's why it's called the epsilon smooth rank. Okay, but you see, these are kind of like these are now theorems. I'm stating them. It's in this where you optimize over encoder and decoder and so on. So this is good. And then once you have established this, you can do the following. Does that make sense? This epsilon error, right? So basically, I'm just like looking at. I'm pretending, right? So if you think of the interpretation, I'm pretending my source was sigma instead of rho, right? And then I'm running the normal zero error coding scheme for sigma. But sigma was very close to rho. And so I'm not making an error that's bigger than epsilon. But the sigma might have a much lower rank and therefore a lower cost associated. I think it's a very kind of clever way of formulating the problem. And now once you have it, you can now say, well, okay, let me do the original Shannon paradigm where I have a source and the source spits out sequences of symbols. And we would now, a better way than thinking of it sequentially is thinking of many sources in parallel that each spit out one symbol. And now again, I have of course I have my so this is like A1 and A2 and A3, right? And AN. And I have my reference systems, okay? Imagine the reference systems, so I can put them in green and I put them down here, all of the reference systems, right? They're all kind of like going along down here to the end. And I'm now putting all of these in some big encoder. I'm doing some block coding. Then I'm doing a combined storage of it. And then I'm doing a decoding. And then out of the decoder, I get all of these systems again. Okay. And we know from Shannon theory, right? Somehow from Shannon's Shannon entropy, we know that what we really should get is some kind of normal entropy out of this, because we have this identically distributed setup, and this is what happens. And you can now you can see it in the following way. What happens is you just say, well, what is the description of my source? Well, the description of my source is instead of rho A, it's now rho A tensor N. Right? So if I want to understand the compression of rho A tensor N, I should make a histogram of the eigenvalues of rho A tensor N. But the eigenvalues of rho A tensor N, we understand very well. It's just the eigenvalues. Well, okay, what are they? It's if you take an example and you just think of one eigenvalue like a binary system, and the eigenvalues are lambda and 1 minus lambda, and say lambda is the bigger one. Okay, So lambda is bigger than a half. Right? Then the biggest eigenvalue is actually lambda to the n, right? The next biggest eigenvalue will be lambda to the n minus 1 times 1 minus lambda. Right? And how often do I have it? I have this guy n times. Okay, this I have once, this I have n times, and so on. And then I have one really big block. And in this big block, it's actually the eigenvalue that's lambda to the lambda times n times 1 minus lambda to the 1 minus lambda times n. Yeah, so what's the eigenvalue?
It should be binomial distribution.
Yes, but that's the value of the eigenvalue, right? So what happens?
What at the power k times 1 minus lambda power n minus k.
Yeah.
Yes, but the largest one, the value that where I have most of them, is where k is equal to lambda times n. So, right, it's like I'm throwing a coin, and then how often does it, come up heads? So this is my k, absolutely, yes. Okay, very good. So, and then how often does it appear? It's n. It's actually n choose n times lambda. That's the binomial coefficient. And so this is all of these, and then we have some smaller ones. Okay, and all of the mass lies here, and of the stuff where it's close by. Okay, there lies all the mass. With all of the other mass together. Okay, now look bigger than it is. All of this other mass together, it's actually for large n. It's like epsilon. It's like very small. So, and how many of those eigenvalues do I have here? Well, we can do Stirling's formula, we can do other things. It's roughly 2 to the n times the Shannon entropy of this lambda, this distribution lambda 1 minus lambda. Okay, so it's because, right? I mean, if you take well, here it's really n choose, right? N lambda and 1 minus lambda, if you think of it in binomial coefficient, and then comes the Shannon entropy comes out as the size of this, as the growth, right? It's the growth of this coefficient. Make sense? Yeah. Okay. And what you see is that, well, I mean, I certainly should, the other stuff is small. I just cut it off, but I have to preserve the mass of this whole thing, like all of these things. And then, well, the size I need in terms of number in terms of this is the dimension I need, but the log of that dimension is n times the Shannon entropy. So we can cast it into a theorem.
And Shannon entropy is just the probability average of log of probability.
Yes, I will exactly. Yes. Yeah. Okay. So what is the h of lambda 1 minus lambda, right? That was just minus lambda log lambda minus 1 minus lambda log 1 minus lambda. But of course, the generalization of an arbitrary, vector of eigenvalues lambda is minus sum over lambda I log lambda I, and the theorem, and this is really like Schumacher model formulated, is that the cost is that the limit of epsilon going to 0 of the limit of the block length going to infinity, and then the cost per, right? The cost per symbol, so is the cost at epsilon error, right? For this whole thing divided by n, right? Because the cost, like depending on epsilon error for producing for the source where Entanglement, so that's the definition, okay, of this asymptotic setup is equal to the these lambdas here, and then, well, that is what typically is called the phenomenon entropy of rho A, right?
So you divide it twice by n, right?
Yes, I'm sorry, yes. Okay. So that is the typical situation you have in Shannon theory, that you have this cost definition, which always will look like this, something like that. There is an error you're tolerating, you're shooting the epsilon to 0. There is always a block length, you put it to infinity, and then you want to have a formula for the result. And in this case, it's the entropy, and in the quantum case, you'll be able to formulate it as a property of the reduced density matrices.
If you make an intermediate limit without sending it into 0, what?
You can do that. You can do that, and then you will get some quantity that's going to be very close to this. And this is a topic of in Tensor study somehow, if you want, of exactly having these limits properly done, and having there's a book, if you're interested, by Marco Tomamichel, where these things are very precisely and nicely done, this formalism of these Renyi entropies. So and the asymptotic equipetition, the next order, you know, like the square root deviation to this large n behavior is correctly done, etc. So that's very nice if you're interested in, absolutely something to look at. Okay, good. Now I'm wondering what I should do. I think there's two options. We can do what time is it? I can do more. I can explain one more, a generalized, so it'd be natural to now go and take a little more general setup, and then you will see somehow the difference between, so here are two inequalities that you have to prove, right? You prove something is equal, and in one side you prove that you can do it, right? And this is what we focused mostly on, like how do you do the coding, what you project on, and so on, which tells you that this cost here is smaller than the entropy. And there is the converse part, which says you can't do better. And for you can't do better, I usually kind of like did now some hand waving, more hand waving, but I think it's sort of like fairly clear in this setup that you cannot do better, and so on. But I didn't formulate it properly, so.
But can one think of the theorem as a kind of semi-classical limit of the quantum theory?
I guess you can, some sense. I think from a mathematical point, there's connections to the semi-classical limits here.
But the parameter is whatever n, right?
N is the analog of inverse Planck constant.
Yes, I mean, I think there, if you're interested in this connection, I think there is work by Madeleine Guta, which has studied it in this way of, like, for instance, identifying quantum states. So you could also ask, maybe slightly different setups, but where it's like the semi-classical limit comes out more naturally. So I think, yes, it's mostly in what people would call a state estimation. So if you look at the problem of state estimation, then this is sort of most clearly as formulated as a semi-classical limit. In this coding theory, I maybe have a bit of a trouble of, I think though, when these asymptotic equipartition theorems are done for these Renyi entropies and these limits are calculated, then when you look at the second order correction, you should be able to see this limit. You should see this connection to semi-classics. All right. Yeah. So this is one way, and maybe I will finish that story now. We have a bit of time. So, do you want me to finish at 1:45 or at 4 hours?
It's a little bit negotiable, right? Because it depends.
I think now I got you into this setup. I want to continue a little bit on that setup, and then maybe at the risk of not reaching so much of what else I prepared. But I have the feeling that we got quite deep into understanding the setup somehow. So it's natural. So there is some there's a setup that you that is called state merging, which is a generalization of this, which connects now to quantum communication also. So I have a wire, I put the reference, right? So now we're like all happy with that, right? I don't have to write the source anymore. I have Alice, right? Alice is sort of in control of her space here. Okay, so Alice holds system A. Okay. And Bob, he has a system B. Bob lives below the line, Alice lives kind of above, but she doesn't have access to the reference. The reference is over there. And now Alice wants to give A to B, right? So she wants to communicate A to B. Before you can, and she wants to do it by sending as little information as possible across the divide, right? She has to pay for sending stuff from here to here. And before we looked at the same setup, right? We looked at the setup in which B had nothing. B had nothing, and Alice was going to compress it, give it to Bob, and right, and then he would decompress it. So, and we would pay for how much the compression was, because then we would send across the divide. Make sense? But now Bob has information. He has side information. And so the entire description of the system is now given by psi ABR, right, tripartite state. And it's clear that if Bob had nothing, we're back to psi AR. It's a setup from before. So it's a generalization of the setup. This was looked at and solved in 2005. This is Hordetsky. This is M. Hordetsky. There is Oppenheim. And Vip. And then reference goes here, right? So now if we do it a little more formally, then what can Alice do? Somehow Alice does some, right? She does some encoder, then she sends it across. And Bob takes it, but he has side information. He can use it to jointly decode. Okay. And then at the end, he should end up with somehow AB, right? And maybe what goes along the wire, we can call it C. Okay, and ideally, right, at the end of the system, I now have rho ABR, and I can do the same criterion as before. I run rho ABR to be epsilon close to the original one. Okay, so So as soon as you've made the step, you know, of like buying into this into the setup, it's all like very nicely formulated. And what is the answer? Okay, so it's clear, like you know, we're going to jump over the step of the zero error correction. We're going to immediately understand that we want to take the limit of psi, you know, psi will come in n copies, and we want the limit on the copies, and we're going to take epsilon to 0, and before that we're going to take the block length to infinity, and so on. And then we could so we can look at the costs, right? And what is this? What is, or maybe we call it the rate. We call it the rate right away, right? Because it's sort of like the cost. I kind of used the word the rate, which means this is the cost per copy of n, right? It's the cost per. So I want that rate, and that rate turns out to be equal to the mutual information of A and R, actually. And the mutual information is the entropy of rho A plus the entropy of rho R minus the entropy of rho AR. Okay, it's nice. It's kind of very nice, right?
And this is all of them. There, I take a trace over B, right? Rho, for instance, rho AR is a trace over B, and so on.
Yes, I forgot factor half. Yes, exactly. Yes, so here I take a trace over B and R, I take a trace over A and B, and here I take a trace over B. But you can reformulate it, right? Because the entropy of rho A is the same as the entropy of BR. Right? So if you have a pure state on a composite system, the entropy on one side is always like the same as the entropy on the other side. So we can actually formulate it as like, I don't know, only in terms of A and B if we want, you know, and we keep that A, and then we take here, we call it AB. And then here we subtract the entropy of B. Okay, that's another way of writing it. Okay. Yeah, that's very nice. So you can imagine like how do you do this? How do you do it? So there are two parts to the theorem, right?
But those things, they are always positive, right? Or whatever.
Yeah, the mutual information is always positive.
But do they satisfy some other properties?
Yeah, I mean we can. I can illustrate in a minute, but yeah, okay. So maybe I illustrate the formula first. So the I mean, first what we have to convince ourselves, right, is of course that it's a generalization of what I told you, what I promised you before. And maybe the best way of seeing it is if now, right, we said if rho B is not there, right, it means rho R and rho A, they're both identical, right? Rho A and rho R have the same entropy. So this is the same, and rho AR, well, I mean, B is not there. Rho AR is in a pure state. So this is 0, and this is the same. So it's the entropy of A, just as before.
But to be optimal, should we cost maximize or minimize?
And what?
Going back to costs.
Oh, minimum of the cost.
Yeah, but then here, mutual information is optimal is to make it as big as possible, right?
No, it's a fixed state. You're thinking out of Shannon's theory where you have to optimize over something.
Yeah. So we need the rate should be as to be optimal. Rate should be maximized, right?
No. This is just the setup depends on the state psi. From this state, I just compute psi AR. This is not a quantity I will optimize the right hand side. This is again a theorem, not the definition of the rate.
Yeah, I understand. But our goal
is to minimize the communication. You minimize the communication.
It's counterintuitive in data transmission, right?
But it's but data transmission is a different problem, and there the solution contains a maximization. Here, the solution to the problem contains no maximization whatsoever. It's fixed. Okay, there's no Yeah, the rate has a minimization in it, yeah. Okay. Okay, so let's first do some intuition on these entropies. So entropies, especially for up to 3 systems that are nicely illustrated with help of so-called Venn diagrams. So if I take A and R, and I'm thinking of this circle of meaning the entropy of A. Okay, so this is like the entropy of A, and this here represents the entropy of R, and then the joint entropy is of AR, right? That's the entropy of AR. That's the joint entropy, and then you see that when the circles are apart, then the joint entropy is the sum of these entropies, and you see immediately that the middle here, that is this mutual information of A and R. Right? That's basically like this plus that, and then when I subtract this one, it's one's left in the middle. So that's a nice way of illustrating. So if A of R, it's also, you immediately see it's positive from this, and if this is 0, then it's really a product. Then rho AR is equal to rho A tensor R, and if yeah, and then you can investigate. Okay, very well. So the way, okay, so there are 2 ways of proving this theorem, right? So what's the proof? How does the proof work? You have to first prove that the rate is achievable, so that it's bigger than, that it's smaller, right? So the minimum is smaller than this. So this is usually called, this is called the coding theorem, right? This is, you have to do some coding. You have to construct something, you have to construct some encoder and a decoder, right? And then you have to show that the communication is smaller than that, right? That's called the coding theorem. That's where the hard part is. In some sense, that's usually where the hard part is. And how does it do? I mean, how do you do it? Well, I mean, it's like what we had before. You identify somehow a typical subspace, you identify what you have to cut off, and then you have to decompress it here. It's just a little bit complicated because you have the side information. So you have to somehow do something joint. And actually, there was also an ingenious step. It's called the decoupling theorem. And in quantum information, people have noticed that the way to achieve the best understanding of coding is not to try to send the information, but the best way of understanding is to make sure that after the coding step, you're decoupled from R, from the reference. It's kind of like really, it took years. I mean, it took a decade or 2, maybe even more, right? To really fully grasp that what you should try to do is make sure that A has no correlation with R after that step. Because then if there's no correlation with R, the thing really, you know, it lands down there. So this is sort of what people have tried to do. So this happens in here. So and it uses actually kind of random coding techniques. So you throw the subspace at random and uses actually a Haar measure and on the unitary group to do this effectively. Right? To effectively find the random code. So whereas classically also you choose random codes, maybe more in a combinatorial way, random coding in quantum is really like analyzing the Haar measure. So
what you do is the Haar measure. What you do is the Haar measure.
Well, I mean, you basically have to your encoder is you build it as an isometry, so you as a traced out isometry, and this isometry has then 3 dimensions, namely an input, and then output goes to C, and an output goes to nothing somehow. And you have to, if you have to find the right way of choosing the dimensions here, then you choose the isometry at random, and the random isometry will have the correct properties to achieve it. Okay, that's what you have to then then find. So harm measure and the so-called decoupling theorem are the keywords there. And then I think but I think you can sort of like see that this would get very technical now. Okay? We need another lecture to introduce decoupling and doing the harm measure and all of these random coding techniques, and then we would get here. But you have somehow seen the idea. The idea was still together with this cutting off, right? You also need to do that, right? Of course, you need to cut off to right subspace and right dimension. You have the epsilon n. It's kind of like tricky. You have to get used to it. So it's very technical. But you got that idea from the other part. But here's an interesting thing, which is this direction. Okay? And so you want to show, once you have achieved this, you want to show that you cannot do better. Okay? You want to show that no procedure whatsoever for encoder and decoder will outperform you. And like very often in converses, use monotone functions. Use some kind of function, in I don't know, in topological stuff, you would say like invariance, right? Or you use some kind of invariant, something that stays invariant or behaves somehow monotone in the right way. And then somehow if that monotone function is tracked properly, it will sort of like, it will give you an obstruction, right? So it's, I don't know what's your favorite monotone function there, but for instance, I'm thinking of like knot theory and the Jones polynomial, right? If I find that the two knots and the Jones polynomial is different, well, then I know I can't transform this one to the other one, because while I'm doing the Reidemeister moves, right, the Jones polynomial will stay what it is. And here it's like it's the same idea.
What is monotone here?
What is monotone here? Yeah, well, you have to now find the monotone. Maybe you can guess. It's not hard to find. What is the monotone I should track and understand for this? What is the monotone that could be an interesting monotone?
Monotone under what?
Under the protocol, right? So I'm sort of like I'm tracking. Yeah, maybe someone has an idea. Otherwise, I can of course say.
Probably, I'm not sure they understand the question.
Yeah, so you imagine that somehow there is a starting point for the protocol, and there is an end point in the protocol, and in between something happens. The protocol runs according to certain rules, like an encoder, communication, and decoder, and the question is somehow which rates or which C is necessary, and I want to show that the C has a lower bound, and so I want to find a property of my system that changes while I'm doing the protocol by at least like somehow the size of C. Okay. I will do it and you will see, but okay. So what I have to track, you see, it's about correlation. So what I want to track is actually the correlation between Bob and the reference. Okay. So Bob has a certain correlation with the reference before the protocol, and he has a certain correlation with the reference after the protocol. And I want to understand how this correlation behaves. And you can see that somehow the correlation will be invariant when the correlation between R and B will be invariant whatever Eve does here, Alice does here, right? So, and this is kind of like the difficult part, right? So part of the difficult part, and then I only have to understand how this correlation with R and B changes when something is communicated. And then again, once it's on B side, I mean, not much is going to happen. That's the idea. Okay. So we track the correlation between Bob, and it's important that it's Bob, right? Because Bob has, in the beginning, he only has B, and then afterwards he has A. So it's not between B and the reference, between Bob and the reference. Okay. So what's our qualification for the correlation? Well, I mean, we have only one measure of correlation. I explained it. That's the mutual information between R, right? I said, okay, the mutual information, this quantity has the property that it's zero if it's uncorrelated, and it's like it's high if it's correlated. So let's track that. Okay. So we look at what initially, right? So initially, the correlation is B and R. Okay, whatever B and R have is initially. That's the correlation. At the end, well, the correlation is actually because the Bob has the entire system. So it's A, B, and R. Actually, I have to check that. I'm not telling you. I think it's the right way. Yes, okay. And now I only have to understand how much does correlation increase when I send a qubit across. Okay, so certainly if Alice sends a qubit to Bob, the correlation between Bob and the reference can increase. But if I can bound how much, and the bound is is that for every qubit, okay, this you have to prove separately. So there is a lemma, right? We need. We'll put it up here in the corner. Okay, the lemma says that for every qubit that arrives at Bob, his correlation can only go up by 2. Okay, so mutual information. Maybe I put it in the formula. Huh? I say like mutual information of the reference and B, okay, and Q, okay, is smaller than 2. Well, this is a qubit, say qubit 2 plus the mutual information from R and B. And you know, we're gonna have to do it. This is homework. Okay, it's going to be a homework. That's our lemma. Okay, so if you communicate a qubit to Bob, at most this mutual information can go up by 2. Okay, that's the lemma. And then, well, how many qubits are being communicated?
So that's if Q is whatever independent of R or something.
No. Regardless of what the state of the choice is.
When is it exactly 2?
When it's exactly 2
Yeah.
is when when the joint state of Q and B, Q and R is so rho A, rho A R B Q. Okay, when this is when R actually when R consists of an R1 and B tensor, and then it has this maximally entangled state. So it's a you know I didn't normalize it now, but in dimension 2, okay. So I think then it's maximal. So if the qubit is maximally entangled, because then before I have this, right? Okay, so then it is okay. Is it? Yeah. So then because before, if the Q was not there, this is just the identity and it's uncorrelated with this, has no effect. So it's just the mutual information here, and then afterwards it has an entangled pair. An entangled pair has mutual information too, right? Because it's maximally mixed here and it's pure overall, and then it's without this factor of half, it's then 2. Okay, so this would be the things. Okay, so this is like equality if, right? Equality if, right? This is sort of like a bracket, right? It's true in general, but it's equality if we have the situation. Then Okay, good. So now you know, now it's easy, right? Because we communicate, right? I mean, right, how much do we communicate? Well, we communicate so, well, the end, right? We now take the lemma, and we, you know, the end is we have this, and then we know that it's what was at the beginning, and then how much we communicated, right? How much we communicated? Well, that was our rate. And actually, the rate was the number of qubits we communicated. We have to multiply it by 2. Okay, because that's 2 times the number of qubits. Okay, and this gives us now a lower bound on the rate. What is the lower bound on the rate? So this means that the rate has to be. You see, this suddenly you get lower bound, right? So now this way you get lower bound of a half times the mutual information of A, B, and R minus the mutual information of B and R. Okay, and then you have to do some gymnastics with these things, right? Okay, but it's not that much, right? So there's like the entropy of.
But that is IABR. This is an entropy, whatever, of something.
Well, this is the, you see, this is the joint entropy. This is the entropy of the individuals. Of AB plus the entropy of R.
Which means in total that's the entropy of R.
That's the entropy of R. Yeah, we have to now do this calculation. Minus the joint entropy, but that's 0. Right? And here we have minus the entropy of B. I mean, I hope it comes out right. Minus the entropy of R plus the entropy of BR. Okay. And then this is entropy of R. Here we subtract it again, okay, so this one goes with this, and then this here is the same as the entropy of R, and then I think, and this here is the entropy of, this is AR, right? Yes, so this is the entropy of, this is the entropy of A, BR is entropy of A, entropy of B is the entropy of AR, okay? And then you got the formula. Okay, so, but I think what I really wanted to show you is that these 2 ideas. We've got both ideas now, the coding theorem, and I think this is it's quite good.
So do you want to give us a short list of what didn't that you right you
What
said
I didn't do.
yeah, what you didn't do.
Yeah, so
just
to get you an idea. Yes, so what I wanted to tell you, okay, so maybe what I wanted to say, and maybe a couple words about this. So what are now the what are now next steps, right, for this? And this was 2005. Of course, people have continued, and we have already touched upon a few things. One was, say, second order asymptotics, right? Really getting this precise. Another thing that people focused on is doing multi-party coding, and there's new difficulties arising that also don't arise classically. I think you already kind of like see maybe that what has changed in the past 2 decades is really that we got the quantum solutions to the problems. So really this decoupling theorem, the quantum entropy, and all of that. And then say Holebo-Schumacher-Westmoreland was very much still like classical coding, trying to make it quantum, the classical coding. But now we're really in the quantum realm and R measure and decoupling, and we have the right tools. What I personally have been interested in is making the encoder and decoder. So they consist of a circuit, and I explained what the circuit are, and showing that things still work if these circuits have noise. And this is so it is combining the topic of fault tolerant computing with communication theory. And it's also something that has not even been done classically, because classically it's not needed. So classically, our phones are perfect. They work perfectly. They compute. All the computing devices, the encoding, decoding devices are perfect, and the noise all lies between us and the router. And so this is one thing that I've been focusing, and this is not something we have in the quantum realm. Quantum realm, we really have qubits that are very noisy. We believe they will be noisy in the decades, maybe forever, but in decades to come. And we have to understand how to do this technique still. And it can be done, but it requires a whole new set of tools. So I've been going in that direction. One can prove fundamental theorems. So for instance, you can prove that such a setup still works if the encoding decoding device has noise. And not noise that like vanishes when n goes to infinity, but noise that stays there at the K level. So right, this part has connections maybe on the mathematical side to representation theory, which I haven't explained. This is also something that I've been playing around a lot. The reason is that you see that, for instance, properties that come out here are eigenvalues of these operators. So many of the concepts are not basis dependent. And when it's not basis dependent, well, then you could use codes that new type of codes that are rotationally invariant. And that leads to using representation theory, using Schur duality, using other kind of coding techniques. So this is also part of where I've been working on. And I think this is sort of the major areas. What I was going to say in the second part is I wanted to go, you see that all the correlations was always between two parties. Okay, we tracked the correlations. As I said, B Bob and the reference, and we looked at rho A, B, and so on. And the question really is, what can you say when you go to multi-party? Okay, so what happens to entanglement and properties there to multi-party? And there it becomes complicated and maybe more complicated in a certain way. And so I wanted to speak about that part because then somehow we've been speaking in the break a little bit about maybe very briefly, we've been speaking in the break about pure states and like how entangled are they, and basic qualifiers of entanglement that you have already seen. Right, I have said that a state is entangled if it's not a product. Right. This is of course a property you can, and then we can quantify entanglement by saying how many of these products do we need to do it. Right. And we come to notions of rank. And then if we have multi-particles, then from notions like this, we come to notions of what's called tensor rank. And tensor rank is a very interesting property that comes up then in these studies. So you can do tensor rank, and you can again. So I've been, in some way studying this year, but these generalized ranks and tensor ranks. And what is very interesting there, and I think I spent a lot of time on, is then to understanding the asymptotics of these points. Okay, so, and this is already difficult in the zero error setting, right? So before I told the zero error setting, it just came out as the rank of the density operator, was still kind of like easy, right? And then we had to do it became difficult when we did the epsilon. Here, things are difficult already in the epsilon equals 0 case, but one can still study this asymptotics, and it has a number of connections, and maybe you notice it already has asymptotics to algebraic geometry. And why? Because when you look at the properties of the rank, they don't change under GL locally. And so you then get algebraic geometry. When you do combinatorics, and then when you take this tensor n, sometimes they get a combinatorial flavor. So they connect actually to the subsets. And I was very thrilled to see that this is a combinatorial object that Terence Tao has been blogging about, and there was and then there's some other properties called slice rank. So these are ways of quantifying entanglement. And I was thrilled to see, so at the research station next to the blackboard, there's a bunch of games. And there is the game set, which is actually solving the combinatorial problem of the capset. So I encourage you, whenever you're in Diablo Day, take this game. It was a lot of fun, and it's really directly related to studying entanglement and understanding how these properties happen asymptotically. So
I guess it's a classical game, right?
Yeah,
You're saying
it's a classical game, but sort of like you can study the asymptotics of the game with the help of encoding it in a tensor, and it's all classical, but then you are faced with exactly a problem like this, and you can then study, for instance, monotones. So the capset problem is, in some sense, is the question of how you can now convert this into tensor product of unit tensors. How many diagonals you can extract from this tensor, and the rate maybe theta of n at which you can extract diagonals. So these are maybe diagonals of, I don't know, size 2 diagonals. Okay, take a tensor product of this. So how big a diagonal object you can find in this tensor, and these are combinatorial questions. You can study them with this, and of course, once you have like some quantum intuition about these tensors, and then these correspond to some fancy tensors, so then you like to play. But it was a lot of fun playing the capsets. So combinatorics, geometry, algebraic geometry play into this game. A little bit of symplectic geometry also. I guess with connection to algebraic geometry.
Okay, well, thanks a lot. So, any questions here on Zoom?
Yes, sir, a very naive questions. When you talk about this many particle entanglement, what's kind of roughly, or what's a roughly number in your mind?
So that's a good question. So sometimes I think of 3.
Okay.
Okay. And then you can look at n copies of it, and n is arbitrarily large. And in this sense, the 3 particles just get the gigantic dimension. Okay, this is one way of thinking about it. I mean, the number 3 is sort of like a small fixed number, right? So you can also take 8 or something like that, but it's not growing with n. What you can also do, and maybe that's something I forgot to say, is that you can take these tensors, of which you have a good understanding now with, say, these techniques, and instead of taking a tensor product like this, you can combine them in a tensor network. And then that connects, of course, to condensed matter physics, and maybe in some sense also to descriptions of, say, neural networks that also have descriptions that are very much like that.
Okay, thank you.
So you roll it. I like to kind of think of them as I actually like to think of them as being associated to the edges of a graph. So if you think of just a normal graph, and then you could think of the edges having a certain dimension of being these normal EPR pairs, call them, or these associated to the edges. And then you can also go to hyper edges and associate, say, states like this to hyper edges and so on. So I like to think of them as like a hypergraph to which I associate certain states with the hyper edges, and then you can capture different phenomena.
All right, more questions?